You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that had, has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you.
Hello, this is Richard Jacobs with the Future Tech and Future Tech Health Podcast. I have Tom Coughlin, president of Coughlin Associates. He's a widely respected digital storage analyst and a business and tech consultant. He got over 35 years in the data storage industry with various engineering and management positions. He has a bunch of publications and 6 patents to his credit. He's also the author of Digital Storage and Consumer Electronics, The Essential Guide. And we're going to talk about something unusual today, DNA and digital storage. So, Tom, thanks for coming.
Thanks very much, Richard. Looking forward to talking to you.
Yeah, so tell me, what's the premise of being able to store information using DNA?
Well, DNA is, of course, what our own genetic information and that of all life on Earth is stored on. And there actually have been, people have been able to recover DNA from old species and basically potentially reconstruct or at least learn a lot about those creatures. There's even talk about using old DNA, say from woolly mammoths that were frozen in the tundra, to eventually recreate such animals. So DNA seems like it's a means of natural molecule that can store information for a fairly long period of time, as long as it's kept in the right conditions. So I think that's kind of the initial inspiration. The other part of it is that the tools for being able to create DNA, write it, as well as to read the information on the DNA, or read the sequences of on this DNA have improved enormously since the first full genomic analysis was done in the early part of this century. And so the prices and the time it takes to write and read information, in the case of doing digital storage, is going to be a synthetic DNA, not natural DNA. Those costs have gone down to the point where people are starting to consider that as an option for keeping information, and especially for keeping digital information.
Can you give me a comparison between what it cost to first sequence the human genome and storage capacity, and the cost and the speed now?
Yes, the first ones were enormous. There was like a huge government project and also private projects costing many millions of dollars in order to get the first genomic sequencing. And now I believe the costs for genomic sequence are around $1,000. And there's projections that would get in the range of $100 without too long a period of time, which also, of course, will have great benefit for personalized medicine that's based upon the person's actual genomic makeup. And so the thing that's really driving a lot of the development of that technology, in fact, is the medical profession trying to create personalized medicines based upon utilizing your own genomic information to tailor drugs and processes that may benefit you individually. Maybe have fewer side effects as well.
Yeah, so if you were to compare storage on current digital media, how long does it last before it gets corrupted, and what's the density of the storage capacity versus DNA? How long can it be stored, and what's the density?
DNA potentially can store very, 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 very high densities of information. But again, there's a lot of a lot of things need to be done in order to enable commercial DNA storage, and we're still in the early days of such things. But the potential capacity is maybe 1,000 times that what's currently achievable with modern storage technologies. Probably hard disk drives are maybe the example particular for that. So it has a lot of potential.
Could be 1,000 times as dense, approximately.
1,000 times as dense, yeah, somewhere in that range, I think.
How would that be possible? What allows it to do that? What is it? Just the way it's stored, or what is it?
Well, we're talking about volumetric density. So if I have strands of DNA, I could pack them into space and have a much synthetic DNA and potentially have a much higher bit density per volume, like per cubic centimeter, than I could with say hard disk drives or with flash memory for that matter, but magnetic tape hard disk drives for instance. And so that's the potential advantage is that I could have one of the potential advantages have a high volumetric density, some proven, under the right conditions, proven longevity of information. Now, it's not to say that there won't be probably unique means by which bits get corrupted and that you won't need to put in some kind of parity and some error correction in recording the information. That's highly likely that you'd have to do that, and it's going to have its own unique bit rot characteristics and things of that sort. So, interesting thing about DNA, one of the really interesting things about DNA storage is if I write a DNA sequence, I can write like 1 million copies about as fast as I can write a single copy. So if you want a lot of copies of a piece of information, this would be a way of making that. Everyone could have their own piece of this information on a piece of DNA if they wanted to.
Well, why is that possible? What is it about DNA that allows you to make so many copies so quickly with no more time than one copy?
Well, in fact, that's how they purify DNA, is they get a strand of DNA that they want, and then they create multiple copies of it. So a lot of the technology that they developed is to create large amounts of a DNA sequence in order to magnify that for other work that they want to do on it. So it's just one of the characteristics of how people work with DNA that they can do that. So potentially it has that capability that I can make an awful lot of copies of a piece of data on a synthetic DNA. Now, writing it is not necessarily fast, but I can make a lot of copies. And likewise, reading is not very fast. And part of that whole getting the cost down, both potentially for digital storage applications and also for these medical applications, is increasing the throughput of DNA, both writing creating DNA, writing it, and also reading the DNA, being able to decode the sequences. And those speeds, people are putting a lot of technological development work and R&D into improving those speeds. A lot of being driven by the medical applications, potential medical applications, but it also allows for the possibility of lowering the cost of writing and reading data on synthetic DNA, and therefore being a viable storage means. Like I say, we're still in the early days, but in 10 years' time, there's some possibilities that, particularly for a passive archiving type application, that DNA could be an option. Synthetic DNA writing and reading information could be an option for long-term passive storage. That is information that you don't access all the time, that you could keep that on synthetic DNA sequence.
What happens in a typical hard drive? How is information stored, and how does it become corrupted if it's sitting there? I thought it would, just forever be stored, not become corrupted.
Now, well, so we all face the laws of thermodynamics, and entropy tends to increase. Entropy being disorder, and so there's thermally activated. So the way that the hard disk drives work, and there's similarities in the way that almost any kind of digital storage technology is going to work, is that in the case of hard disk drives, we're using magnetic fields to read and write information. So you have something called a head, which generates a magnetic field, and also will be able to read back magnetic information off of the magnetic media. And the magnetic media rotates underneath of these magnetic heads, which read and write information on concentric tracks on a disk surface, and that's how you read and write the information. And there's also circuitry for doing signal processing, extracting the data. There's special coding that's done in writing the data that gives you some amount of repetition of data, so that if there is some either noise during the read or write process, or if there is some minor corruption of the data, that you can still recover. There also are processes for going through data when it's not being used and making sure it's okay and rewriting it if it's having trouble. So, but what happens is, and this is true of any means of storing information, is that thermally activated processes, in the case of the magnetics, it's the random reversal of magnetism of the very fine grains of material in the case of a hard disk drive on the disk media surface over a period of time. So there's some random reversals happen over a period of time. If enough of that happens, it would tend to cause problems in some areas in the media, and therefore your signal will degrade, and eventually, if that continues, you won't be able to read information, or you'll lose pieces of information. So a key element in any kind of storage technology is to build in redundancy, to build in error checks, and occasionally to go through and make sure the data is okay, and to rewrite it if it needs to be rewritten in order to recover the data or make it so that it will last longer. But it often requires some kind of active management to do that. Now, true of hard disk drives, is true of magnetic tape. It actually is true also of semiconductor-based technologies like flash memory, that over time, data has a tendency to degrade, and so you need to actively rewrite it and move it on. That's sort of the natural phenomena. The other thing that happens, of course, is what's called technology obsolescence, which is the technologies that we use to read and to record information have been changing over time. For instance, how many people nowadays have the tools to be able to read a tape, cassette tape, for example. Back in the 80s, 90s, there would be a fair amount of technology to do that, but a lot of people don't have that anymore. This is for small cassette tapes. And so as technology changes over time, and that can be the recording technology itself, but also could be even more important, the interfaces and even the software drivers that enable the devices that can read and write that information, those technologies may change. So another factor in terms of trying to keep information for the long term is, in addition to natural degradation of information that can occur if you don't intervene and try to catch it before it happens, the other thing is the technology that you're using can become obsolete, and that can even be software itself. So actually carrying information into the future, into the long future in particular, has a lot of requirements behind it. And so there's people that are working on interesting technologies where, for instance, they will essentially archive a package that contains, for instance, the information about the original software that created it, that one could create an emulation of that software in order to be able to recover the data. That gets rid of some of the, if you will, the sort of metadata constraints. But the other thing, of course, is physical interfaces, things like that. For instance, 100 years from now, will there be such a thing as a USB interface? Will my old USB be able to plug into that and work? So these are, in terms of long-term storage of information, whatever the technology, there's definitely things that need to be considered in trying to bring data in the future, and there's definite challenges in doing so.
So what are some of the I mean, you kind of said it, but what are some of the current roadblocks with storing information on DNA, and where would the DNA be housed, and how can information be retrieved from it, when needed?
Sure. So there's a number of companies a number of startups that I've run into and done some work with, some of them that are looking at using DNA for storage of information. Some of them basically they're just going to create a DNA strands. You dry them out essentially, and then when they're dry, they can remain stable for a fairly long period of time under controlled conditions. And then you reconstitute them and put them in a reader, and you can read back the information. Not a very fast process, but that's one way in which people are looking at doing it. There are also, and I can't go into too much detail on it, but folks that are working on actually using semiconductor technologies. And there's a lot of work being done, for instance, by an outfit called IMEC, which is in Belgium, which is a nanotechnology and electronics research center in Leuven in Belgium. And they've been, and there's other people as well, have been doing a lot of work on building, for instance, microfluidic and electronic devices on silicon. So sort of nanotechnology, MEMS type devices, microfluidic devices, building with sensors, building with electronics, and actually be able to, for instance, move fluids around inside of a silicon matrix. And there are people that are looking at using that kind of technology and building read and write capabilities essentially on a chip basis, and saying that they can achieve very high densities of information storage with certainly a higher data rates, both in read and write that you could get from that more passive approach where I just dry it and then I have to reconstitute it and read the DNA again. So the DNA essentially stays inside of some cells on a chip from which they can be written to or read from over time. So there's some fascinating ideas that people are working on, which again, they're in the early days, but they offer a promise that we may add DNA to some of the other digital storage technologies that we are used today. And in fact, in many regards, I think if you consider all the new solid state memory technologies, as well as flash memory, which has been around for a while, hard disk drives, tape, we can add DNA to the mix. And essentially, we're just getting the whole storage memory hierarchy is becoming even more complex and more specialized in terms of how we may use these technologies together or singly for accomplishing different tasks.
So what's going to be your specific role? Are you investing in startups, or what are you specifically doing in this area?
So what I've done in this area right now is, so first of all, I'm a storage analyst. So I'm always interested in what people are doing with any kind of memory or storage technology. So I love this stuff. This is my bread and butter. And so I write on technologies. For instance, I just finished a report recently with a colleague on emerging memories for artificial intelligence applications. But I also do consulting, and I work with startups and other people in terms of technologies and how it might be implemented. So I've done a bit of that with some of the DNA storage folks. And I love doing this kind of stuff because it's so fascinating. First of all, digital storage has allowed, essentially, it's the enabler of modern civilization, processing, storage, and networking. And everything we got nowadays is digital, and that all has to be kept somewhere. And so all applications essentially are dependent upon various types of digital storage and memory technologies. So that's the kind of stuff I deal with. That's what my interests are. I also put on some events in this area. In fact, I've got a workshop with a professor at Stanford I'm doing on August 29th that's on emerging memories and artificial intelligence. Sorry, the report I did actually was on, I think I may have misstated that earlier, so I want to correct that. But the report that I did recently with a colleague was on emerging memories, their development, the market, and also capital equipment in order to be able to manufacture them. But I'm also doing this workshop on August 29th at Stanford with a professor there at the Bechtel Center, which is going to be looking at various types of emerging memories and artificial intelligence. And that includes, there's some interesting AI interactions with these emerging memories, like examples are phase change memory or resistive memory, where they're actually using them as emulating, to some extent, the way that nerves in the brain work. And so they call it neuromorphic computing. It's sort of a spike-based process, an analog computing process that they're using these memory cells in order to be able to enable, and it emulates the brain. And so there's really fascinating things people are doing, applying technologies like that, as well as other technologies for deep learning, machine learning, convolutional networks, all of these related applications. And
how would a set of stored data be different if an AI was interacting with it, and if it emulated more how people store data in their brains? Like, would the data set change over time in prescribed ways, or with certain elements highlighted, some might be diminished?
Yeah. So what they're doing is they're actually using memory technologies. And the particular examples that are being used are what's called resistive memory and phase change memory. And they're using them as sort of analog processing units. And so they process information in a way that's related to the way the brain does it. And so that's that's essentially what they do. Now, there's other things with these emerging memories people are doing that's called neuromorphic computing, and may be very useful, especially for training applications where you're actually training an artificial intelligence. In the case of actually using that stuff in the field, there's a process called inferences, which is done where they take a training model that's already been created. Now I'm trying to apply that to say images captured in the field or voices, so I can do image recognition, voice recognition, things of that sort. And the technology used for that is called inference. So they have these inference engines which need weighting functions that represent, for instance, characteristics of sound or characteristics of an image that it can then process using the algorithm developed during the learning process in order to say, in this camera, I'm seeing a dog, I'm seeing a car, things like that, say if I'm an autonomous vehicle, or recognizing somebody, the voice of somebody or something of that sort. So a lot of IoT type applications that want to include artificial intelligence, what they're doing is they're either in the endpoint device or at the edge close to it, they're going to be having these inference engines. And these inference engines have to have weighting functions that are stored in memory. And what they're looking at, especially if I have a battery-powered device, that non-volatile emerging solid-state memories like magnetic random access memory may be an option to include in these devices, because I can save power because they don't have to refresh the memory all the time like I do with volatile memory. But the other thing is I can turn them off and I'm not using it. So I have a lot more ways of reducing my power usage and therefore increasing battery life. So those are some of the interesting things.
What about on the initial storage? I mean, there's data streams that are so large that it just wouldn't be practical to store all the information coming in. So what about a discriminatory function that's on the front end of a storage unit that is using AI to say, all right, store this, don't store that, store this, don't store that, and deprecate this. This is more important. Kind of work with the data and dynamically store it and change it as it's taken in.
Yeah, I think maybe the prime example of that would be, let's say I have an autonomous car that's in a connected network environment in a city. So I have something, say, called a smart city. And I have a lot of, let's say it's 5G network or something like that. I've got intelligence, actual processing power at the edge, say at cell towers or even even more distributed than that. And the car itself takes in a lot of data. It's got, they're talking about these things generating maybe a terabyte of data a day. But most of that data is meant for immediate processing and analysis, because the car, if it's going to be able to help you to drive or drive itself, it's got to make split-second decisions. It can't wait for the latency of going over the network. So it does a lot of stuff locally, and that might be with an inference engine. But then there's results of that analysis, or the commands that the car gives that it wants to share with the outside network, so that, for instance, that car and all the other cars in the area, I may have a network that keeps track of what cars are doing or warns another car, there's a car that you can't see right now, it's around the corner that he's going to be driving through an intersection, right? And so it can warn another car and help to keep accidents down and that sort of thing. So it's going to require both intelligence capabilities and some learning capabilities, of course, at the edge or in the device themselves, as well as in the data centers. So the big data centers, the cloud. So what we're seeing, actually, it's kind of interesting. There's like this eternal back and forth between centralized processing and distributed processing, and I think with the growth in AI and the sort of requirements that we're moving back into a distributed computing environment where there's going to be essentially processing all over the place. And that's what enables a lot of these IoT and autonomous driving, or any kind of, or even in factories, enabling Factory 4.0, where I've got robots that make a lot of decisions themselves. They're working directly with human beings, rather than restricted areas. So they've got to be friendly to humans. And that this distributed computing environment that's using these artificial intelligence algorithms of various sorts, and doing both learning and training, and also application of those models, the inference engines, that kind of thing, that all these things are going to be very distributed, and if we're going to generate more data than ever before, and some of that data is going to have to be kept. And that's where the storage comes in and the memory comes in for the short-term stuff.
Any other? Can you give just a few details on any other storage schemes that really were surprising to you, or you have a lot of hope in, or you think they're going to be like really instrumental in the future?
Oh, there's a lot. If anything, we're getting the storage options are more complex. I mean, they're greater than ever before, and it's an interesting thing. I think it has to do with the fact that as human beings, we're natural storers of information, and it's our brains work by getting layers and layers of information, and that's what's created culture, is the handing down of information. So we're naturally information processing creatures by our nature, and the options and means by which we do this seem to be increasing over time. So I keep track of things that are going on, always looking for notices of this or that. And there's always seems to be about every 2 or 3 weeks some new storage technology that oftentimes the university will announce and says it's going to take over everything. And it's done in glass with holograms, or it's done with some kind of weird semiconductor technology or other. So there's enormous creativity that goes into trying to create new ways in which we as information processing creatures, new ways in which we can capture and understand the world around us and ourselves. And so I think there's enormous creativity there, enormous demand, and I don't see it ever diminishing. I think it's just the nature of who we are. And there's some. Yeah, go ahead.
Anyone trying to data mine literally someone's brain, their neurons, their neural network? I don't know what you get from it, but have you seen anyone that's trying to do something like that, to emulate it and or download it somehow?
So I'm actually a volunteer with the IEEE. I'm currently the president, actually, of IEEE USA, but I've been involved in an activity in IEEE technical activities that's called Future Directions. And there is an initiative in IEEE Future Directions. It's actually called the Brain Initiative that has been working. There's a number of different groups and organizations working on that, the actual brain to electronics interface. And I would say that we're not too far off from practical. In fact, there are some practical applications of that kind of technology, particularly to help people with disabilities. Let's say to allow somebody to communicate with an artificial hand using their muscles in their brain, their neurons. But even more complex things are in the works. And I think, which I think also is going to drive some interesting consequences in terms of personal privacy and the demand for such. And legal requirements, but we're probably within decades of being able to essentially read a person's brain, which may allow people, for instance, to, if you will, to create an artificial telepathy where one person can read the mind of another person, or one person can send his thoughts to another person or device, through electronics without speaking. But there may be even further things, and there's all this discussion of deepfake technology right now, right? Where they've got, I can create things that, images and videos and stuff that I can't tell what's real or not. Imagine you could do that by projecting directly into the brain, right? So there's going to be some interesting legal and ethical implications of these technologies in the future, and how do we use these things, and what's the right way to use it? What are human rights in an age of such technologies, and how do you protect freedom, and how do you know what's true? And probably one of the things that may eventually happen is something along the lines of people have a right to know the truth, if you will, the ground truth, that what is real, actually real, physically real, versus what is what is represented to them. So interesting implications of all these things, but there's a lot of people working on technologies, which of course be done for good or for ill, in terms of their applications. But hopefully that we'll be using these in order to enhance life and enhance the way we work with each other and get along with each other and make progress and do new things and have adventures and fun.
Excellent. So any milestones that you think are realistic that are coming in the next 1 to 2 years that you can mention? Or personal things that you're working on that you think will come to fruition, at least an early version of it in the next year or two?
So one thing's interesting. I just is that actually I was at the Semicon conference, and there was it was an AI event put on by Applied Materials. And Applied Materials makes semiconductor manufacturing equipment, particularly used for a lot of things, but memory is one of the big drivers of semiconductor spending. And one of the things they were saying in 2018 was the first year that more data was generated by machines than humans, and that trend is only going to continue. So I think our machines and our devices, all the IoT devices, etc., we are users of data, as I said before, kind of by our nature, but our machines now are generating more data and will do so increasingly in the future than we have. So I think human beings have specialized oftentimes in creating information, okay? And I'm sort of looking at the future. Information, it's so hard nowadays to, for instance, read all the literature that exists, but I could see the day that we create machines that can gather all the information generated in a field or in related fields, help us to, with human intervention and direction, synthesize that information in order to create new types of knowledge and new ways in which to create wisdom and understanding of things that probably will exceed anything we've ever had before. So I think
that would be amazing. Imagine if you could have at hand all the knowledge in a given field, and you see it dynamically updated in real time, and then you can make inferences from it, and anything new that you think of, you can check it against that whole corpus of knowledge. It'd be amazing. It
would be amazing, and against collaborators, both machine and human. You know, in other words, we're still going to be a need for a technical community, for people who their livelihoods and their passion is to know things, but we'll have new tools for which they can do it. And perhaps even, who knows, maybe some of these humans will not be of organic form. We'll have to wait and see what happens there. But I just see fascinating possibilities in the future. And, one of the things that's really cool this year was, the last few years, for instance, I'm bachelor, my original degree was in physics, but the black hole event horizon imaging work, and the other thing was the gravity wave detection that have been done within the last 3-4 years. Fascinating ways to see new things about the universe around us. And that's been enabled by developments of technology, in terms of our processing power, in terms of storage and memory and networking, and our ability to build stuff that's ever more complex and interesting. So we know less than we will ever know. It's probably true whenever you are, but I think we know a few things. We know stuff, but we don't know everything, and there's a lot more that's out there that will be fascinating and will keep humans and our tools working to understand, for I think centuries to come.
Very good. Well, Tom, what's the best way for people to get in touch and to find out more?
So you can find out about me at tomcoughlin.com, and I've got information there on who I am and reports I do. If you look up Emerging Memories and Artificial Intelligence, you can find out about our August 29th workshop at Stanford. And my email is tom@tomcoughlin.com if you're interested in this and want to talk more on things. And I'm a frequent speaker. I write a lot of stuff. I do a regular blog on Forbes.com. I did that book on digital storage and consumer electronics. And I also do a lot of stuff in IEEE. So, if you're involved in IEEE, you probably run into my name as well.
Very good, Tom. Well, thanks for coming on the podcast. I appreciate it.
Thank you very much. I appreciate your inviting me to come.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you.